We're going to color code these. So if you're writing the equation, so now here's our a value. And so this one would be 0.5x squared. Second one would be 2x squared. Third one here would be negative 0.5x squared. And finally, we have negative 2x squared. So now when we go to graph these, if we start with the blue one, 0.5x squared, what we might do is we might do a table of values, because that's sort of the basic way that you could go about graphing this. So you could think about, well, on my original graph here, I have the point 2 comma 4. What happens now when I plug in x equals 2? Well, 2 squared is still 4, but now I'm multiplying by a half, so I get the point 2 comma 2. And you could do a bunch of table of values points as well. You might also think back to grade 11 and say, I know this is a parabola, I know the vertex starts at 0, 0, and that a value in front, we learned either made our graph wider or narrower. And with the 0.5, you might have remembered that made it wider, so I went over 1 up a half, then over 1 up 3 halves, because the original red graph went over 1 up 1, over 1 up 3, and now we're cutting that in half. So we could get that our blue graph has the same shape as our red graph, but it was wider. And when we get to our green graph, well, it's also a parabola with a vertex at 0, 0, but now we go over 1 up 2, over 1 up 6. For example, you would get the point 2 comma 8 now. But you could also use a table of values to figure that out as well. If I plug in 2 for x, I get 8 for y. And so our green graph is narrower than our original red graph. Using either what we learned yesterday with reflections or using what you learned last year with parabolas and negatives, that negative out front meant that it opened down. What we learned yesterday is a negative outside of the function is a vertical reflection. So it would have taken our original red graph and flipped it down. With the 0.5, it gets flipped down and multiplied by that 0.5. So it's exactly like the blue graph, over 1, but now we're going down a half, over 1, down 3 halves. And same thing with our black graph. It's reflected over and narrower as well. What we're going to look at in this course is, well, what happens to certain points? In this case, we're going to notice that with that number in front, that number is outside of the function. And so far, with our translations and with our reflections, we've learned that everything that's outside of the function has affected things vertically. It's affected the y-coordinate. And if we look at the coordinates I've labeled here, we can see the same thing. Each time we had a new point, our y-coordinate had changed. And so, for example, going from my red graph to my green graph, I multiplied my y-coordinate by 2. And that makes sense or connects to the equation because there was a 2 out in front. So we have points on our original graph and corresponding points on our new graph. And what's happened is our y values here have been multiplied by 2. So we're going to look at, well, when does it affect our y-coordinates? When does it affect our x-coordinates? When do we stretch our original graph? When do we compress it? And we're going to use the word stretch whenever we take like our red graph to the green graph is going to be a stretch. Can you imagine pulling it away from the x-axis? Stretching it away from the x-axis. Our blue graph here, we would call that a vertical compression because you imagine taking that original red graph and pushing down on it or compressing it towards the x-axis. And then you would get the blue graph. So on the next page, if you turn to it, we're going to look at each of these separately. They're all square root graphs. And we're going to put a little note This first one, our a value is outside the function, and that means that it's going to affect the y coordinate. And we're also going to look at what are some of the notations and how are we going to show our work for questions like this. Because with translating it, it was mainly pretty easy. You could just shift it. When you stretch something, the shape changes a little bit. It's like steeper or flatter than it was before. We still have, in each of these colored graphs, we still have the curve of a square root graph, but it's changed a little bit. So here we have 5 graphs. The red one, the square root of x, is our original graph. And if we look on our original graph, they've labeled the point 16, 4. That makes sense that that point is on our original graph because the square root of 16 is 4. So starting with the blue graph, what we're going to show is we're going to say, here's a point on my original graph, and if I take that point on the original graph and I draw an arrow to say it's changing, how is it changing? Right above there, I'm going to write how my point is going to change. Since it's a y equals 3 square root of x, that 3 is outside of the function, we know that it's going to affect our y coordinate. What I'm going to write above this arrow is what I'm going to do. I'm going to multiply my y coordinate by 3. Well, what happens to the point 16, 4 as a result? It's now going to be, if I multiply my y coordinate by 3, 16, 12. Notice that's the point on my blue graph. That corresponds to the point on my red graph. If we look at our green graph, again, we have the point 16, 4. This time on our green graph, what are we doing? There's a 2. It's outside of the function. We're going to multiply y by 2. And if I just write y by 2, you can probably tell that it's multiplying. So that you can do that to be a little bit shorter. And if I multiply y by 2, that point is going to go to 16, 8. And sure enough, that's the corresponding point on that graph. We'll just do one more. We'll do the purple one. So if I start with 16, 4, on the purple graph, there's a 1/4 out in front, so we're going to multiply our y value by 1/4. That's going to result in the point 16, 1. We would describe the blue graph and the green graph as vertical stretches because we've taken our red graph and stretched it away from the x-axis to get our new graphs. We would call our purple graph and the orange one vertical compressions. The purple one, we would say, that's a vertical compression by a factor of 1/4. Because we've multiplied our y values by 1/4, that compresses it. So whenever our values that we multiply by are bigger than 1, those will be stretches, and whenever our values are less than 1, those will be compressions. So if we look at the next example, this time we've got a b value inside the square root. So we can make a note that this is inside the function. And because it's inside the function, everything inside the function so far in all of our transformations has affected things horizontally. Same thing here. Now this is going to affect the x-coordinate. Again, our red graph is our square root graph. That's our parent graph. This time they've decided to choose the point 4, 2 to compare it. 4, 2 is on our original graph. So if we start with our blue graph, we see a 4 inside of the square root, and because we just did our y coordinates, your gut is going to tell you, let's multiply x by 4, because that's what we did with y. But just like translations, you know with translations, when you move to the left, there was a +3 inside or something like that. When you moved to the right, it was a -2. Up and down was exactly like you saw it. Like if it had a +3 at the end of the equation, you moved it up 3. If it had a -5 at the end of the equation, you moved it down 5. But inside was the opposite. The same thing happens with stretches and compressions. We're not going to multiply x by 4. We're going to do the opposite. The opposite of multiplying is dividing. We could write divide by 4, but what we're going to do, because dividing by 4 is the same as multiplying by a quarter, what we're going to always do is multiply by the reciprocal. You can think of dividing by 4, but sometimes we're going to have fractions inside, like 2/3. It's going to be easier to think of flipping that fraction and multiplying than it will be to think about dividing by whatever the fraction is. So what we're going to say is we're going to multiply by the reciprocal, which is the opposite. That's like dividing by 4. And what's going to happen to our point? It's going to go to 1, 2. So we notice, sure enough, that's the point that they have labeled on the graph. If we go to the green one, we start with the point 4, 2. In the green graph, we have a 2 inside the function. So we're going to multiply our x values by 1/2. And 4, 2 will change to 2, 2. And sure enough, that's the point that's labeled. Again, I'll just do one more. We'll do the purple one. 4, 2. Now we have a 1/4 inside. If I do the reciprocal, we're going to multiply x by 4, and that's going to change that point to 16, 2, which corresponds to that point there. Language-wise, in the purple one, we would say this is a horizontal stretch by a factor of 4. So whenever that value inside is a fraction and we do the reciprocal and we're multiplying by a number bigger than 1, we're going to say that it's a stretch. The way that a horizontal stretch works is it's like you're grabbing that red function and pulling it away from the y-axis. So any point that's on your y-axis gets fixed, and you grab that red graph and stretch it out horizontally. For the blue one and the green one, those would both be horizontal compressions. Because we're multiplying our x value by a fraction, the blue one we would say is a horizontal compression by a factor of 1/4. And it's like we took the red graph, fixed it on the y-axis, and squished it towards the y-axis. And we would end up getting the blue graph. Now, some of you might look at these graphs and say, how do I know that the red graph to the blue graph, couldn't you also like stretch it vertically and have it match up? Yes, sometimes that's the case. Sometimes a compression horizontally might match up with a stretch vertically. In fact, I think the blue one is a great example of that. Could you simplify the equation in the blue one? What's another way that you could write the square root of 4x? Yeah, square root of 4 is 2. So I could write this as 2 root x. If it's written that way, the 2 is now outside of the function. If I thought of it that way, then I would think of a vertical stretch. If I think of the 4 inside the function, then I have to think horizontal. So depending on where the numbers are, affects how you think about the equation. So had we thought of it as a vertical stretch, what would happen to the point 4, 2? You would multiply the y coordinate by 2. And if I took the point 4 comma 2 and multiplied the y coordinate by 2, I would get the point 4 comma 4. And sure enough, that point is on our graph as well. If I went way over here, look over here. Sorry, I have the point 16 comma 4. If I did a horizontal compression and multiplied the x coordinate by a quarter, I'd still get 4 comma 4. So we'll get the same points depending on which way you're thinking about it, but sometimes equations can be that way. You can see them as horizontal compressions or as vertical stretches, depending on how you've written the equation. For the most part, we don't do a lot of simplifying. We just look at the numbers and how they're given to us and work with it that way. In the last example here, we have both of them combined. So again, what's going to happen is you're going to take a point, and the original point they've given us this time is 4 comma 2. And in the blue one, and we'll look specifically at the blue one in this case, we have 4 square root of 2x. So we have a 4 outside of the function and a 2 inside of the function. And if we're wondering what's going to happen to our point 4 comma 2, well, right above this arrow, we're going to describe what we're going to do. When I see that 4, does that affect the x or the y? That affects the y. Are we going to multiply by 4 or 1/4? Everything outside of the function is exactly how you see it. The one thing you're going to find in this unit, it is so easy to mix these things up. There's not that many concepts that we learn, right? There's like 4 concepts that we learn that are all very similar. You mix 2 of them up, and all of a sudden you get 50% of your quiz wrong. So it's scary that way. We really have to focus on the details. With the 2, that's inside the function. Things inside the function sort of act opposite of what we see. So in this case, we're going to multiply x by 1/2. So our point, x by 1/2 is going to go to 2, y by 4 is going to go to 8. So we notice that we have the point 2 comma 8. What's going to happen is you're going to be asked to graph y equals 4 root 2x completely. So the way that you're going to go about doing that is you're going to say, I know what the square root of x graph looks like. That was the graph in the top left-hand corner of that activity. These are the 3 key points that I know. I know it's going to go through 0, 0. I know it's going through 1, comma 1. And we already know it's going through 4, comma 2. So what you're going to do is you're going to look at not only one point, you're going to say, well, another point originally was 0, 0. What happens to 0, 0 when I multiply by 4 for the y coordinate and 1/2 for the x coordinate? Well, that's some pretty easy mental math. It's going to stay at 0, 0. What's going to happen to the point 1, comma 1? 1, comma 1, I'm going to multiply x by 1/2. That's going to be 1/2. I'm going to multiply y by 4. That's going to go to 4. And so now I would know I have 0, 0 at 1/2, comma 4, and 2, comma 8. Those 3 points corresponded to our original 3 red points, and now we would be able to draw our graph going through those points, still having the same shape as our original square root graph, kind of a curve bend, but it's much steeper than it was before, because that graph had a vertical stretch by a factor of 4 and a horizontal compression by a factor of 1/2. So these are some square root graphs. On your next page, they look at some cubic graphs. They're saying if you had a 1/2 x cubed, you're going to have to decide, is that 1/2 inside with the x or outside without the x? And this is where you're really going to have to concentrate, because that 1/2 is really close to that x. Is it inside the function or is it outside of the function? Well, the function cubes things. That was our original function. Is that 1/2 getting cubed or is it not? It's not getting cubed. And because it's not getting cubed, that 1/2 is outside of the function. And since it's outside of the function, you would be multiplying your y values by 1/2. And it would be a vertical compression. Can you see that that red graph, if you went above it and below the x-axis and took that red graph and squished it towards the x-axis, that you would get that green graph? And if we had a y equals 2 to the x, this orange graph, can you imagine that red graph grabbing it above the x-axis and below the x-axis and pulling it away from the x-axis, that your red graph would get stretched to become your orange graph? And if you looked at particular points, so they've got the point 2, 8 on our red graph. When you stretch it vertically, I have an orange pen? Yes, I have an orange pen. When you stretch it vertically, that point becomes 2, 16. You've multiplied the y coordinate by 2. And on our green graph, when you multiplied your y coordinate by 1/2, it becomes 2, 4. And because we're multiplying our y coordinates by a value, what happens is we can combine what we did yesterday with what we're doing today, algebraically. Because yesterday we flipped over axes, either vertical reflections or horizontal reflections. And algebraically, when you flip something vertically, you multiply a y coordinate by -1. When you flip something horizontally, you multiply the x coordinate by -1. So if we look at this next example, where we've got y equals -2x cubed, that will be, outside of the function, a vertical reflection, and the 2 will be a vertical stretch. So there's 2 transformations that are happening. But if we think about the point, so here's our point 2, 8. What happens to that point is we're going to do, for the reflection, multiply y by -1. For the stretch, multiply y by 2. Can you see that you could put those together and just multiply y by -2 all at once? And sure enough, on the green graph, that's all we've done. We've taken our y value and multiplied it by a -2. Okay, so they have the official explanation of this here. What you can pull out of this is just that when you have a value out in front, what's happening is your y coordinate gets multiplied by that value. This is talking about all of the abstract part, about when that a value is in between 0 and 1, we call that a vertical compression. When you're multiplying by something bigger than 1, we call it a vertical stretch. So if we do example 1 right now, here we have a graph, and it's given to us in function notation, y equals f of x. So it's given to us in function notation. We want to sketch the graph of -1/4 f of x. So the new image graph is also given to us in terms of f of x. But now there's a -1/4. We have to decide, is that -1/4 inside the function or outside of the function? In this case, that -1/4 is outside of the function. It's not inside where the x is. So because it's outside of the function, it's going to affect things vertically. The negative, that's going to be a vertical reflection. The 1/4, I'll just do abbreviations here, that would be a vertical compression. Okay? Algebraically, we're going to combine both of those things and say we're going to multiply our y values by -1/4. To see what that does, we're going to take some key points from our original graph. Well, first of all, the most important point on this graph looks like this one, this 0, 0, because that's where it changes direction. So I'm going to look at what happens to 0, 0, and I'll write above this arrow what I'm doing when I multiply my y coordinate by a -1/4. Well, again, this is pretty easy mental math. 0 times -1/4 is still 0. So we're going to get the point 0, 0 also on our image graph. We need some more points to finish this graph. I could choose 2, 2, and it's not bad, but then when I multiply by 1/4, I'm going to get a fraction. Now, I love fractions. Some of you, maybe not so much, but I do love fractions a lot. However, when I'm choosing to do mathematics, often, if you can avoid them, it makes nicer looking answers. So I might not want to choose as a second red point 2, 2, because when I multiply that y coordinate by 1/4, I'm going to get a fraction. What would be a nice point to choose? So when I multiply y by 1/4, I don't get a fraction as an answer. 4. So if you chose 4, 4, let's see if that works. You'd get 0 here, and when I multiply 4 by a -1/4, sure enough, I get -1. So this point right here was a nice one to choose. Now I'm going to make a mistake that I'll say almost all of us will make at some time in our life, and I want you to see if you can see what mistake I did. Okay? I want to, oh, jeepers. That's not the mistake. The x didn't change. I don't know why I wrote 0. It should have been 4, -1. Does that make better and more sense? Okay. You will also make that mistake in your life, just writing down a wrong number for whatever, for no reason whatsoever. Your brain just decided to play a trick on you, and you're like, I wanted to write a 2, and someone said something about 5 o'clock, and you just wrote a 5. You don't know why. That will happen as well. But this is the mistake that some of you are going to make. I'm going to plot this point 4, -1. No, I'm not going to go in the wrong direction. I'm going to go to 4 here, and then I'm going to go down 1, and I'm going to plot that point. What did I do wrong? When plotting that point 4, -1, what did I do wrong? Yeah, the scale's going by 2s. But we get so used to counting grid marks by 1, you might miss that. So it actually should be right there in between. Right? Can you see yourself doing that? Oh yeah. Okay? Every day, all day, I'm going to do that. So just be careful with that. Okay? Sometimes the scales are given. 90% of the time when the scales are given, you're going by 1. It's to train you, oh, just count by 1s, count by 1s. And then every once in a while, it goes by 2s or by 4s or something else just to screw you up. So pay attention to that. If I wanted to do another point, another nice point, hey, I could do this one over here, 8, -8. If I did that point, no, sorry, -8, 8. If I did that point, and I multiplied my y values by -1/4, I'm going to get -2. So I'm going to go just down here. I can now connect my dots, and this is my new graph. Can you see the vertical reflection in your new graph? Can you see the vertical compression that it has been squished towards the x-axis? This question also asked us to state the domain and range. So So the domain and range of our original function, well, the domain was everything. Our range was bigger than or equal to 0. And on our image graph in blue, our domain is still everything, but now our range is less than or equal to 0. Since your domain and range are x values and y values, whatever transformation you did affects them as well. So if I took this range and I multiplied my y by -1/4, does this make sense that instead of being bigger than or equal to 0, when you would multiply by a -1/4, it would be less than or equal to 0? The 1/4 doesn't matter because 0 times 1/4 is still 0, but the negative flips it down. Now, this question was given to us in function notation. Do you recognize that graph? If you wanted to write the explicit equation of our red graph, what would it have been? What graph is that from our activity? Absolute value of x. So we could have got this equation, the same question, with this notation instead of function notation. And then when they went to ask the blue graph, they wouldn't have said -1/4 f of x. They would have said -1/4 absolute value of x. So just be aware of those different notations. Is the question any different when they wrote it this way? No. You're still asked to do the same thing. You're still asked to multiply your y coordinate by -1/4, but now they're giving you the actual equation rather than function notation. And sometimes you'll get this question without the graph given to you. They'll just say, consider the graph of y equals the absolute value of x, and then you have to be able to create that graph from memory or from a table of values, figure it out, and then graph the new one based on that. Okay, our question for practice on this one are number 3.